Hi everyone, and welcome to the section 4.8 video. This is going to be the start of the last unit in the course, and it's going to be the base, this unit, for pretty much everything you're going to do in Calc 2. So you're still going to need derivatives. All of that is also part of the base, but this is going to give you kind of the second half of the two main ideas of calculus. So the big thing here is antiderivatives. So anti and derivative. So just before you even get started, let's remind ourselves of what a derivative is. I have a function f, and then I'm able to do a derivative and get f prime, right? This action here is called the derivative. And we have rules for it that we developed. We defined it using a limit, and it was a little tedious, right? But then we learned a bunch of rules, and it made our life easier. And then, from there, I could just give you all these different functions, and you could just find the derivative using those rules. So, what is an antiderivative? An antiderivative is us answering the question, well, can I go like this? Can I start with the derivative and just knowing that function, like forget about f, pretend I just gave you f prime. Could I then do something to reconstruct f? So the derivative, you start with this function and you're able to build this one using our rules. Okay, well, can I go the other way? Can I start down here? Can I know the speed of something? And then can I do something that builds this function? So here I have the position function of an object. If you want to go the physics-y route, I can construct the speed. Antiderivative is saying, actually, I know the speed of something. Can I construct its position just from knowing how the speed is changing? There you go. That's the antiderivative. So antiderivative is, can I go backwards? That's it. That's the whole idea. So what is calculus? Well, calculus is derivatives, and can I go backwards? Antiderivatives. Done. So those are two cornerstones of what you're going to be doing in calculus. So what we're going to have to do is, just like for derivatives, we're going to have to go through and we're going to have to figure out, are there rules for this? How do we apply them, practice them, all that kind of stuff. We're also going to have to talk about, okay, with a derivative, there was some geometric meaning. So when we first talked about derivatives, we didn't just say, here's a function, I'm going to define these rules, I'm all done. We started off by saying, actually, the derivative itself, we connected that to the slope of the tangent line. So we really started with this idea of, here's a function, I can draw a tangent line, and then we built the derivative out of that, the connection there, the geometric connection. And so we're going to spend some time in Chapter 5 building what's called an integral, which is very closely connected with the antiderivative. And we're going to build it using area, and that's going to be this geometric thing. What's happening here? So for a derivative, we're thinking, okay, this gives me slope of a tangent line for this function. An antiderivative, that's going to connect geometrically to area and the function itself. So we're going to have two ways of going about this, just like derivatives. What are the rules? How do I do it? And then also what does this mean, at least geometrically? What's the picture I can think of? For antiderivatives, and what we'll get to in Chapter 5 with integrals, we're going to do the same thing. What are the rules? How do I work with this? And then also, what does this mean graphically? What can I get out of doing this? Why am I doing this? So, quick overview of how antiderivative connects back to what we've done. So what's the actual definition? It says a function big F. So this is capitalized. That's the general way we write an antiderivative, is this capital F. So be careful when you're writing capital versus lowercase. So a function capital F is an antiderivative of f on some interval I. So they're just saying for some x values, if the derivative of big F is little f. So that might seem kind of like a weird definition, but it's just this picture I drew here. So let's write it out. Here's f. This is the antiderivative of little f if I can take the derivative and go from big F to little f. That's it. So big F is called the antiderivative, and again, I'll draw that in blue. This big F is the antiderivative of little f if I can start at big F, do derivative, and get down here. This is the antiderivative. So you could just have this little diagram in your head for how big F and little f are connected. Okay, so that's it. The definition of the antiderivative is, well, can I do the derivative and get down to little f? Yes? Okay, then I must be the antiderivative. Or, I have to correct myself, I must be an antiderivative. Now, that's going to get a little crazy in a second, but we'll do a bunch of examples so you can see why I just corrected myself from the antiderivative to an antiderivative. Not just being English specific here. That's important. So, okay, it's just some function that if I do the derivative, I get to this little f. Cool. Okay. All right, so here is the crazy thing. If f, big F, is the antiderivative of little f, again, it's a lot to kind of hold in your head. Just immediately when you see this line, just draw this. F derivative to little f. Okay, yep, okay, I see the connection. Then the most general antiderivative of little f is this function. So what are we saying here? We're saying that unfortunately, this action going backwards, so taking little f and trying to rebuild big F, this, like, okay, I start here and I go antiderivative. This does not produce one answer. It technically produces infinite number of answers, which is really weird because that's not what you're used to for derivatives, right? So let's go back up to the original picture. I give you a function. Just go back to the last few units. Forget about all this for a second. I give you a function. You take the derivative. You're done. That's the one derivative. That's it. I give you x squared. You give me 2x. There's no infinite answers. It's just 2x. I'm all done. It's different with antiderivatives, and you'll see in a second why I'll give you the reason. But it's not this way. I give you a function. I say take the antiderivative. You can't just give me one answer. You have to give me an infinite number of functions that fit this diagram. There are an infinite number of functions here, big F, that when I take the derivative, I get to little f. And so that can make this a little bit tricky. And there are little things that you'll see when doing antiderivatives where it's like, oh, this is just a little trickier than derivatives. So unfortunately, this isn't like a one-to-one idea of derivative then antiderivative, and everything's going to kind of pass over that you learned about derivatives to antiderivatives. It's not quite that simple, but a lot of what you've thought about and ideas and patterns you've seen hold a decent amount. But the big thing here, the takeaway, is that there's an infinite number of ways to have a big F whose derivative is little f. And that's given right here. So let's think a little bit about this plus c. So like, what's going on with this plus c? C is a constant. So as soon as you ever run into a statement like this, c is an arbitrary constant, well, just pick some numbers. Like, let c be 2, and -1, and pi, and 72 over 146. Just pick some c's, and like, let's think about it. So, okay, let's look at f of x plus 2. Now, if this is supposed to be an antiderivative, I should be able to take the derivative of this with respect to x, just, like what we've been doing. Let's take the derivative of this. Okay, and I should get down to little f. So, okay, take the derivative. The derivative would split up because of the addition into this plus the derivative here, right? This is just all derivative rules. Nothing new right now. Okay, what's the derivative of a constant? That's the light bulb moment happening. I'm pausing for it. The derivative of constant is 0. So this, I can add anything I want here, and the derivative of that is just 0. It does not have any impact on the derivative. All that matters is the derivative of a big F. Well, look at what we said here. It's little f. Right? So it does not matter what I add to this function here, because it does not impact the derivative. So f of x plus 1 plus 2 plus 3 plus 4 plus pi minus 3 minus 7, whatever, all of those functions have the same exact derivative. And the way you could see that pictorially is I've got the function x squared. We'll see in a little bit, we'll do some examples. This family of antiderivatives will be x cubed over 3 plus any number. And what you have to do, let's zoom in on this picture a bit. What you have to just remember is for each of these functions, right, we are trying to talk about each one of these. The derivative of each of these is x squared. And what you need to focus on is just take an x value. So like, let's say 0. Let x be 0 for a second. And you just focus on this line. All of these functions are changing the exact same way, right? Their slope here, 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 here. They're all slope 0. So, okay, maybe I just got lucky. Pick another point. Pick an x value right here. And then draw a little tangent line. Boom, boom, boom. Look, they're all the exact same little tangent line there. So all of these infinite number of functions are changing exactly the same at every x value. What does that mean? If they're all changing exactly the same, what did we say change was? Back in the last few units. Change is derivative. So if they're always changing the same, they all have to have the same derivative. So there you go. This is just a shift, right? Another way to think about this, go back to your pre-calc days. Plus a number is just shifting a function. Take a function, right? Move it up and down. Are you changing anything about the way that function changes as x increases? No, all you did was just move it up and down. You didn't stretch it or compact it or anything else. You just took the function. You didn't bend it or anything. You just move up and down, move up and down. That does not impact how it's changing, right? So when we do an antiderivative, in general, we need to add this plus c, and that's what you're going to have to remember. I know this seems like a lot, but what you'll just have to remember is plus c, and I'll just keep saying that every once in a while, randomly, plus c. That needs to be in your head. You're going to be in Calc 2, and I'm going to be sitting there in your class, plus c. Not really, but I might be in your head, plus c. That's what you're going to have to remember. But this is why, okay? So just think about it. But we'll do some examples right now. So, okay, let's give ourselves some more space here. Example number 1, we'll zoom back in a little bit more, says find a general antiderivative of this function. So, immediately again, I'm looking for a function, big F, such that when I do the derivative, I get down to this. Okay, that's my goal. I do the derivative, I get down to what this is. So let's start off with just a piece of this, because I think once we do 1 or 2 pieces of this, you'll start to see the pattern. So why don't we start with just 1/2? Okay, I want to find a function, f, so we'll just do like a piece of this to start. When I take the derivative, I get down to 1/2. So what's a function that when I do its derivative, I just have 1/2 left? So I'll think a little bit about it. Hopefully it's not too bad to see that in this case, f would have to be 1/2 x. Take its derivative, and you get 1/2. Okay, you're done. So 1/2 x has to be the antiderivative of 1/2. So immediately, this piece here, so we'll do it, we'll color code this, right? This, the antiderivative of this specific number, 1/2, is 1/2 x. So we'll write that down, 1/2 x. Because when I do the derivative of this, I get this number. Okay, let's do the next piece. We'll do this in purple. So 3/4 x squared. Okay, so we have to figure out what this question mark is. What function, when I do the derivative, gets me down to this? And so you just need to rely on the fact that you've done a ton of derivatives. And the key piece here is this x squared. We have to start with something that when I do the derivative gets down to x squared. But remember, squaring, doing the derivative always drops this power 1. So then immediately, I've got to have this, right? I do the derivative and that gets me down to the square. Okay? But here's the thing. Actually try it. Do the derivative, right? Do the derivative, you get 3x squared. I don't quite have that. I have 3/4. So what am I missing? I'm missing a 1/4. Okay, so do the derivative, drop the 3, perfect. So then that gets added in here. X cubed over 4. Okay, and then lastly, we've got this other piece here. We'll do this in green. We've got a negative 4/5 x cubed, right? So we are sitting here. What function, when I do the derivative, gets me down to negative 4/5 x to the third? And again, let's just ignore for a second the constants. We'll deal with that in a second. It's all about this power, right? Get out of here, number 13. So it's all about this power. So x cubed, how do I get down to that? I have to have started with x to the 4th. So okay, now do the derivative. That would give you 4x cubed. Awesome, got the 4, got the x cubed. What am I missing? I'm missing a 5 on the bottom and a negative. So just put that in here. Double check, do the derivative, drop the 4, perfect. So that goes here. And we did it. Ta-da! This is our f of x. Big F of x. Okay, so how do we do the antiderivative here? Each piece, we do the antiderivative of that. And so that, you might want to just, at this point, always be questioning. That's okay. I should have said that much earlier to you, although based on some of the things I've done, like errors on these things, you already should have been like, I got to question Mr. B. But that's good. You should always be. There's a little thing here that we're using. And the thing that we're using is we're using the idea that when I take the derivative of a sum, right, I can break it up. So we're kind of using that in reverse here. So I know we don't have a symbol for antiderivative, right? But what we're using is this idea that if I want to do the antiderivative, right, and I want to do the antiderivative of a sum of things, so little f plus g, I want to do that antiderivative. Well, as we saw here, I can just do the antiderivative of f plus the antiderivative of g. And again, we don't have a symbol for that like we did the derivative yet, but it works the same way. This is the same as doing the antiderivative of f plus the antiderivative of g, right? And the reason it's the same is because, well, the derivative works that way. So to go backwards, I can just do the derivative, and I can do the derivative on each piece. To go back to f plus g, what could I do? I could just take the derivative of this whole thing, which is the derivative of just this, plus the derivative of this. So that's super nice, right? Derivatives break up over addition and subtraction. Guess what? So do antiderivatives. So some of those properties go hand in hand together, which is awesome. We also used a property here when I said, just forget about the constants for a second. Why could I do that? It's because when we're doing derivatives, what do we do with derivatives? You have a constant multiplied out in front. You forget about it for a second. You can move it out of the derivative. So you gotta, those same patterns and things for derivatives are carrying over to antiderivatives. And so that's things you have to kind of pick up on, that those same things that you see are gonna apply. Okay, so just to kind of point out. Now we get to this piece and you might be like, okay, I mean, I guess each piece we did here was fine, right? But how do I know I'm right? Well, this is the best part of antiderivatives. The whole point of the antiderivative, right, is we go backwards here. But what we can do is just circle around here. We should be able to get from little f to big F and big F to little f. So if you're not sure if this is right, take the derivative. We'll just do it kind of quickly thinking it over. Derivative of this, 1/2. Check. Right? That's right. Derivative of this, 3x squared over 4. Check. Perfect. Derivative of this piece, negative 4x cubed over 5. Check. Done. So that's the awesome thing about antiderivatives. You have a way to check it. Do the derivative. Did you get back to where you started? Yep. Okay, then you did it right. So super, super nice thing. Okay, what did we forget? What did I say I was going to haunt you with in calculus? This was one possible antiderivative, right? But we forgot something, because this is not the only one. When you do the antiderivative, what do we need to include? Plus c, plus c, plus c. Remember? Plus c. I have to include the plus c because this is only one possible answer for big F. There are many, 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 infinitely many possible answers. So if I want to do the general, so we'll underline this, maybe we'll do this in a different color, the general antiderivative, that means I've got to get rid of this and add a plus c. Now this is the most general antiderivative, because if I put a number in here, 3, 7, -2, pi, whatever, that function, if I take the derivative, I'll get back here. Just do it. We check that one, check this one, check this one. Derivative of 2, oh, that's 0. Okay, perfect, I'm back here. So general antiderivative plus c. Just plus c, plus c, plus c. Smack it with the plus c, always. We'll do problems where the plus c will turn into something specific. You'll see that in a little bit. All right, let's keep going. Okay, find the general antiderivative of this function, cos theta minus 5 sine theta. All right. You know, you knew we were going to get to trig right away, so this should not be a shock that we're at trig. But it's okay, because everything works exactly the same. So we want to find a function g. This is going to be the general antiderivative, such that when I do the derivative, I get down to little g. Okay. Piece by piece. No problem doing this piece by piece. So let's start, we'll do blue, with this cosine. Okay. So I'm looking for a function such that when I do the derivative, I get to cosine. What function, when I do the derivative, gets me to cosine? Oh yeah, sine. The derivative of sine is cosine. Okay, all done. That piece is done. Okay, so that's it. Antiderivative of cosine is sine, because if I take the derivative of sine, I get to cosine. So, okay, what about the next one? Well, let's do this piece now. So, I want to take the derivative of some function and get to -5 sine theta. Okay, the derivative of what? And again, we can ignore, remember, we can ignore this 5 for a second. We can even ignore the negative, but we actually want to keep that. So what, the derivative of what function, ignore the 5 for a second, just gets me negative sine. Well, how do I get to sine using derivative? Oh yeah, cosine. The derivative of cosine will get negative sine, but I don't have this 5 here, right? Well, just put a 5 in. That's easy. The derivative of 5 cosine theta is negative 5 sine theta. Wait. So then this is going to be what? The antiderivative of this is 5 cosine theta. Okay. All right, so I did this piece. Antiderivative was sine. I did this piece. Antiderivative was 5 cosine theta. But I want the general, remember, the general antiderivative, which means I need a plus c. And we've got it. How do I check that I did this right? Well, take the derivative. The derivative of sine is cosine. Check. The derivative of 5 cos theta is negative 5 sine theta. Check. The derivative of a constant is 0. Check. You're done. So one way you can think about this is you're not doing anything new because you're just relying on the fact that you know derivative rules and you're just going backwards. That's it. So it's almost like it's not even anything new. You just have to take rules and use them backwards, which is tough. It's not nothing, for sure. But, you know, if you've done the work to get these rules in your head, the derivative rules, then you already have the antiderivatives in your head, which is pretty nice. Okay. So, let's try another one. Get some more space down here. Given f prime is equal to this, and we know that the antiderivative, right, we know a specific value. At 1, it's equal to 6. Find f of x. So here is a special one where for a second we're just going to ignore this piece. I'll show you where that comes in a second. But again, what are we looking for? I want to find this function f such that when I take the derivative, I get to f prime. Right? That's the whole point of the antiderivative, is like, give me the function f such that when I take the derivative, I get here. So we're going to do it in pieces again. You'll get quicker with this too. We don't have to write everything out. But for now, as you're working on this, totally fine to, take a little time here. And after this one, we're going to try to see if we can find a general rule for these polynomials. So if you've already kind of thought about that, good. If not, start thinking about it as we do this example. So let's do this one first. So okay, I need to find a function so that when I take the derivative, I get to 8x cubed. So again, what did we kind of see before? To get down to x cubed, I would have had to have started with x to the 4th, right? Because take the derivative here, 4x cubed. Okay, well, so if I was to start here, and you could do this kind of scratch work to the side if you want. And how you do this is up to you, how you want to format it. If you see it nice, some other resource, do it that way. Totally fine. You don't have to copy how I'm doing this. Do the derivative, right? What do I get? I get 4x cubed. So awesome. I got the x cubed, but I'm off by what? I'm off by 8 and 4. I'm off by a factor of 2. So 2, 2. We did it. So that 2 goes here. So okay, that's pretty good. This first piece, to get the antiderivative, so I'm going to write f of x equals, and then the first piece of this we just found out was 2x to the 4th. Because when I do the derivative here, I drop the 4, that's 8x, subtract 1 is cubed. Okay. All right, next piece, blue, 12x. So, all right, what function gets me down to 12x here? Derivative. So again, okay, I have x to the 1 here, right? So I need to start with x squared. But when I do the derivative of this, I'm going to drop a 2 down. So just as the scratch work here, if I put an x squared here, I do the derivative, I'm going to get 2x. But I don't quite have that, right? I'm off by a factor of 6. Okay, so how do we get that in? Let's put a 6 in here. Now these match. 6 times 2 is 12. I get the 12. Put it here. All right. We did it. So we're going to get plus 6x squared. Take its derivative. Check yourself. Take its derivative. That's 12x. Perfect. And then 3. 3 is not too bad. You can do this one in purple, the plus 3 here, right? So what function gets me down to 3? Well, this one's really not too bad to do. 3x. Right? The only way I can get a constant here is if this had been an x to start. So, boom. We've got our 3x, take its derivative, get down to 3. So, plus 3x. And then, because we haven't added this new piece in here, we have our plus c. So this would be the general antiderivative. But I don't have a general antiderivative here. I know that at x equals 1, I want the specific function that has a y value of 6. And there's only going to be one of these. So, okay, how do I figure out the specific antiderivative? Well, this plus c tells me which antiderivative, the shift up and down. This point helps me nail down one of them. So just plug in the point, see what happens. So I'll give myself some space here. Okay, f of 1 is going to be 2 times 1 to the 4th. Again, I'm plugging into the antiderivative. 6, 1 squared, 3 times 1 plus c. That's got to equal 6, right? So, okay, that's 2 plus 6 plus 3 plus c equals 6. Okay, so then you just are simplifying here. The 6's go away. This is going to give you 5 plus c equals 0. So c has to equal negative 5. This is what all these will look like. And then you just put it together, right? At the end, your specific antiderivative is going to look like 2x to the 4th plus 6x squared plus 3x minus 5. All done. So what do we do? Just to recap, if I give you a specific point to use, you just treat it like a general antiderivative, get your plus c, and then you plug this point in to figure out what c is going to be. There you go. So we just found a specific antiderivative. All right. Okay, we got another one here. Let's try it. Do we have enough space? Yeah, we got some space here. Okay. So it says, given f double prime is this, and I gave you 2 points, find the original. So this is going to be a little tricky, but once you kind of see it going, well, it's not going to be too bad. Because this is going to be a two-stepper. Because what does the antiderivative do? So antiderivative, you could think of it as kind of undoing a single derivative. So what we're going to have to do is this. We're going to have to do antiderivative to get to f prime, and then we're going to have to do a second antiderivative to get to f. Which, think about this, it should make sense, right? How do I get from f, little f, to f double prime? Well, I had to have gone derivative, and then I would have had to have gone derivative. So it should make sense that to get from here to here, if I've got to do 2 derivatives, I should probably have to do 2 antiderivatives to get back, right? 2 and 2. Okay, so then we've got to just start this off like we just did all these other problems, right? So how do I do this? Well, I need to find a function, f prime, that when I do the derivative, gets me to this function I know. So we'll start off with just this problem, 8x cubed. Okay, so 8x cubed, how do I do this? Well, luckily, we already did this one, 8x cubed here. We found out the antiderivative was 2x to the 4th. So we're going to do a little cheat code here, right? And we're going to say that we just automatically know this first one is 2x to the 4th. Take its derivative, you're going to get this. And then plus 5, well, we already saw what happens with a constant, right? With the plus 3 earlier, that's just going to be plus 5x, okay? And then don't forget, we're doing the general right now, the general antiderivative. That's plus c. So this is our f prime. Boom. We took f double prime, we did an antiderivative, and we got here. Now, what do we know? We know a specific value for f prime. We know that f prime of 1 is 8, so we're going to use that to figure out c. So f prime of 1 is equal to 2 times 1 to the 4th plus 5 times 1 plus c. That's equal to 8. Okay, so that's what? 2 plus 5 plus c equals 8. So that's c equals 1. So then this plus this come together to give me that my f prime, my specific f prime for this problem, is 2x to the 4th plus 5x plus 1. Now I'm not done though, right? Because I want f. So it's like we just restart this problem now. Let's restart the problem. We need to find a function f so that when I take the derivative, I get to 2x to the 4th plus 5x plus 1. So we know how to do this. We're just going to go through and do each of these pieces. Right? So start with this one. I need a function that when I take the derivative, I get to just this piece. So again, it's got to be x to the 5th. Okay. Now this one is a little trickier than the others because do the derivative here. So do the derivative of this. Just change up notation so you're playing with all the different notations. This is 5x to the 4th. But oh, I don't have that. I have 2x to the 4th, not 5x to the 4th. So I've got to get rid of this 5 and put a 2 in. And that's not too hard to do. How do I get rid of the 5? Well, divide by 5. How do I put a 2 in? Well, put a 2 in. Okay, so I can do that. Put a 2 on top, boop, 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 and there we go. So then to start off f of x is going to be 2/5 x to the 5th. Take the derivative, drop the 5. Oh, they canceled. Get a 4, and you got the 2 hanging out. Boom. Okay, let's do this piece now. 5x. All right. Well, again, I need x squared here so that when I do the derivative, I end up with 2 and just an x. So excellent. X and x. But again, I got this 5 on top now. How do I have that happen? Well, just make it happen. I need a 5 on top, and I got to get rid of that 2. So 5 over 2. So then what is this going to be? This is going to end up being plus 5 over 2x squared. Do the derivative. Drop the 2 down, they cancel. You have a 5 left over. 5, x to the 1. X to the 1. Okay, plus 1. How do I get just a 1? Well, that's got to just be this one here, right? The derivative of x is 1. So, okay, that one's not too bad. So we'll plug that in. Plus x, and then plus a constant, because this is a general antiderivative at the moment. Okay, so then how do I find this constant? Well, I gave you, whoops, too far. I gave you that f of 1 is 0. So we know how to do this. Well, f of 1 is going to be equal to, just grab your function here, 2/5, 1 to the 5th is 1, plus 5/2, 1 to the square power is 1, plus 1 plus c equals 0. Okay, so we just got to combine these, right? So this is going to have common denominator of 10. So then this is going to be 4/10. You can just do this in a calculator too. Multiply by 5, 25 over 10 plus 1, which is 10 over 10, plus c equals 0. Right? So then this is going to be 35 39/10. C is negative 39 over 10. So then altogether, f of x is going to be, let me just go back up here, 2/5 x to the 5th, okay, plus 5/2 x squared, right there, plus x plus negative 39 over 10, which we can rewrite as a minus. Make it a little neater. 39 over 10. Boom. That is your original function f. Now, how do I check that this is right? Well, you know 2 points. One for f prime, which you can plug into those functions to double check. And then also, you can just take the second derivative, right? Take the second derivative of this and make sure that you get down to what we started with, the f double prime. That's it. So a lot of work there, but hopefully it's not too bad. Now, we have this table here that you're just going to want to try to get into your head, okay, of antiderivatives. And so one of these patterns, which hopefully we've been kind of thinking about happening here, which we've seen a lot of, is this x to the n. And so let's talk about this for a little bit. So what do we know for derivatives? Let's start there. Derivative, right? X to the n, the derivative of this, we know how to do this. This is nx to the n minus 1, right? Drop it down, subtract 1. Antiderivative. So the way that you could think about how to find a formula for something like this is just do everything opposite. You're going to be like, what do you mean opposite? I literally mean everything opposite. So let's just compare these two formulas. This one here and this one. What's the opposite of subtracting 1? Adding 1. Okay. What's the opposite of multiplying? Dividing. Okay. And then the only other thing that you have to remember with the opposite is the order. That's tough. The order is also opposite. Okay. What do I mean by that? Well, what did you do here? You took n, grabbed n, and you brought it down first. Then you subtracted. But I said everything opposite. So when you're doing the antiderivative, you change n first, then you bring it down. So see here, we brought n down first, then we changed it. Nope, this is the antiderivative. Everything's opposite. So when you're doing the antiderivative, you first add 1 to the power, then divide. But once you get this formula down, this is it. Every single one of those antiderivatives that we did up here that involved x to a power, go back and check that this is how it works. Ready? This one here. I want to do the antiderivative of this. Add 1 to the power. That's the fifth. Cool. Divide by that number. Look at that. Divide by the 5. Okay, does it work for this one? Add 1 to the power. Square. Divide by that. 2 on the bottom. Okay, let's check a couple more, right? How about this one? Add to the power. 4. Divide by 4. 8 divided by 4 is 2. Boom. Add to the power. We get a 2 here. Divide by it. 6. This is x to the 0. Add to the power, you get 1. Divide by 1. Okay, that one's a little silly, but there you go. So you have a rule for this one. It's literally the anti-rule of what you had before, but it's just a rule to remember. And then all these other ones in here are just us knowing the derivative and us working backwards. So like we said before, we know that the derivative of sine is cosine. So then I know that the antiderivative of cosine is sine. This is not a new table, really. It's almost like I flipped the table, right? What did we have back when we first learned these rules? We had a function which was sine, and then we had another column, the derivative, cosine. All I did was take that table and just kind of flip what columns were which. So you got all these different rules that are good to remember, but all just come from you remembering derivative rules. Really, that's it. They all come from remembering derivative rules. Now, I'll just make one extra comment here, and I'll have you notice that there's one specific function that's missing, and that's the natural log is missing. You're going to get to this in Calc 2. In general, not all, it's not specifically always this, but a general rule of thumb is doing an antiderivative is harder than doing a derivative. And now, it's not here, right? Because once you know one, you know the other, and it's just back and forth. And for e to the x, it's even easier, or it's the same. E to the x, e to the x, e to the x, e to the x. But natural log, we know the derivative of natural log is this 1 over x, right? That's pretty quick. But unfortunately, the antiderivative of natural log is much more. So we're going to need some special techniques to figure this out. So that's what you'll learn a bunch in Calc 2, is you'll start off probably doing a little bit of what we're going to be doing at the end of Chapter 5 over again, maybe not. But you're definitely going to be right away jumping into give me some more rules for antiderivatives. And they'll mirror things we've already done. If I have two functions multiplied, I need a special rule to do the derivative, right? Well, guess what? If I have two functions multiplied, I need a special rule to do the antiderivative. You'll learn about that. Functions composed, we needed a special rule, the chain rule. Functions composed antiderivatives, we're going to have rules that help us there. So hopefully, that's something that will come fairly naturally for all the practice you've done with derivatives. But that's the last thing I'll say is that's something then when you are going to Calc 2. Many of you are going to be doing that in the fall, right? So all of this antiderivative stuff is going to come straight from the derivative stuff you've done. So you've got to get that down. Practice that. You finish this class, practice that between now and when you're taking your course. Keep up with your derivatives. Don't let that slip, because you're going to need that for Calc 2. Okay? So just keep on that. Any of the ones that you're not as good at, just practice those. Get those in your head. It'll make your life in Calc 2 so much easier. You'll be the star of Calc 2 if you can just remember these derivatives. All right, so practice up a bunch of these problems, get used to these formulas, try practicing this formula, make sure these derivative rules are in your head. Any questions, let me know, and I'll see you in the next video.